foundations of deep reinforcement learning, sequential decision-making, and Markov decision processes. If you have heard of agents that beat humans at Go, master Atari from pixels, or steer robots through clutter, they all share one skeleton. Learn by acting, observe what happens, and improve from numeric feedback. This video builds that skeleton from first principles. No codebase required today, but every symbol maps directly to code in Part 2. Start with where RL sits in machine learning. Supervised learning consumes labeled examples and generalizes. Think digit recognition. Unsupervised learning compresses unlabeled structure, customer segments, embeddings. Reinforcement learning is different. Data comes from trial and error, labels are not handed to you, and the goal is to act. The classic mental model is a Pong-playing agent, but the same loop drives warehouses, recommender systems, and large language model fine-tuning. RL is the branch, where the algorithm is also the data collector. Draw the boundary carefully. The agent is the decision-making code, policy in action out. The environment is everything outside total control. The agent sends an action. The environment returns an observation and a scalar reward. Counterintuitive but critical. On a physical robot, the arm mechanics are environment, not agent. The agent chooses torques or targets. Noisy physics executes them. Confusing the boundary breaks debugging. You will try to fix hardware in the policy network. Deep RL feedback is a triad: sequential, evaluative, and sampled, and all three bite at once. Sequential means actions have delayed consequences, which creates the credit assignment problem. Evaluative means rewards score goodness, not correctness. There is no single right label per frame, which forces exploration versus exploitation. Sampled means you see a thin stream of experiences from a vast state space, which demands generalization, often via neural networks. Remove any leg of the triad, and the problem becomes ordinary supervised learning or planning. Credit assignment is the emotional core of sequential learning. Imagine an action at time 1, 9 quiet time steps, then a massive reward at time 10. Which decision deserved credit? The dashed arrow on this slide is every RL student's anxiety. Without machinery, returns, value functions, bootstrapping, or advantage estimates, the agent cannot tell whether step 1 was genius or luck. Every practical algorithm is, in part, an answer to this question mark. Under the hood sits the Markov decision process. Reward R of S and A policy pi, probability of action given state. Transition dynamics P of next state, given state and action. Value V pi of state, expected discounted return if you follow pi. Return GT is the sum of future rewards, discounted by gamma. The Markov property is the memoryless assumption. The future depends on the present state and action, not the entire history. That assumption is what makes the math tractable, and what lets neural networks approximate value over huge state spaces. In code, one timestep is an experience tuple. Read state st, pick action a t call environment step, receive next state and reward. The return gt is the discounted sum of future rewards, gamma to the k times r at t plus k plus 1, summed forward. Gamma near 1 cares about the long game, gamma near 0 makes the agent myopic. Every policy gradient and Q-learning implementation is optimizing expectations of this return. States and actions ground the abstraction. A state is a self-contained snapshot of the problem, a grid cell, a robot pose, a portfolio allocation. S is the state space, ST is where you are now. Actions are how the agent tries to influence the world, moves on a grid, throttle commands, buy or sell. Of S is the legal action set, which may shrink near boundaries or constraints. Design mistake number 1 is a state that secretly hides history the Markov assumption needs. Fix the state, not the algorithm. Transitions branch. T of S prime equals the probability of landing in S prime after taking action in state south move forward, might succeed 80% of the time, and slip left or right 10% each. Realistic noise for wheels on tile. Stationarity assumes those probabilities stay fixed during training. Non-stationary environments, Markets, opponents that adapt, need non-stationary methods. But in the textbook, MDPT is the physics engine written as probabilities. Walk the snippet. T indexed by state and action returns a dictionary of next states and probabilities. Random dot choices samples one outcome according to those weights. The reward function R of state, action, and next state returns the immediate scalar. Same action, different rollouts. That is why RL is stochastic optimization, not a single supervised path. Rewards are carrots and sticks, a scalar goodness on a transition, not a tutorial on how to behave. Dense rewards fire every step closer to goal. Fast learning, but the agent may game the shaping signal and never finish the real task. Sparse rewards pay only at victory. Slow search, but behaviors are less biased by handcrafted hints. R of S, S prime encodes the designer's goal, the policy discovers the strategy. Bad reward design is the silent killer of RL projects. Gamma is the discount factor between 0 and 1, exponential decay on future value. A +1 reward now stays +1. The same +1 5 steps ahead might count as 0.59 at gamma 0.9. By step 10, 0.34. Because the future is uncertain, variance grows with horizon. Discounting stabilizes learning and forces a trade-off. Grab immediate reward or invest in actions whose payoff is delayed. Every return formula you will see carries gamma. Synthesis 1 timestep. The agent holds a policy pi and emits action A. The environment applies transition function T, updates state, and returns next state ST +1 and reward RT +1. Gamma weights how much the agent cares about that future stream. The behavioral loop and the MDP diagram are the same story in different languages. Boxes and arrows on slides, tuples and expectations in code. DEEPLR adds neural networks as function approximators on top of this loop. The ultimate objective: maximize expected return GT, RT +1 plus gamma RT +2 plus gamma squared RT +3, and so on. A time step is one interaction cycle. An episode runs from start to terminal state. The return is the discounted sum across that episode. The agent's sole job is to discover a policy that maximizes expected return in its environment. Value functions, Q functions, actor-critic methods, they are all technology for that one sentence. That is the foundation, MDP, the feedback triad, credit assignment, transitions, rewards, and return. Part 2 implements a grid world agent step by step in Python. Subscribe to Life of Geeks, comment DEEPLR for the coding episode, and scan the QR code for the channel.